In Chapter 5, we'll talk about continuous random variables. So by the end of this chapter, a student should be able to recognize and understand continuous probability density functions just in general. And then after that, we will recognize and follow the following continuous probability distributions and be able to apply them appropriately. The first is the uniform distribution, and the second is the exponential distribution. So in section 5.1, the continuous probability distributions, let's remember a few things. We have a random variable. A random variable is a numerical variable that describes the outcome of an experiment. We usually notate this with capital letters, usually X or Y. And there are two types of random variables. Remember, there's the discrete that we learned about last chapter. These random variables take on all the values and they can be counted. Now we're going to talk about continuous random variables. These can assume all values in a given interval. Right? So this is where we talked measurements, time, money, etc. before. Recall in the discrete probability distribution, it was the distribution that can take on a countable number of values. And for this course, we used a table of all values that the random variable can assume. Okay? And so we put those on the left in the left-hand column, and then the corresponding probabilities of those values on the right-hand column. Now, once we move to a continuous random variables, the values of X cannot be placed into a table since the outcomes are measured and not counted. So we're going to have to use a graph or a function to represent the distribution. So what are the properties of the continuous probability distribution? Well, this graph or this function, so the graph of the continuous probability density distribution is a curve. It gets called the density curve. And the probability that's associated with it now is the area under the curve. So this density curve is also known as the probability density function, which we abbreviate PDF. Right? Lots of times we'll use a lowercase f of x to represent the curve because it is a function that represents the graph of that distribution. Now remember, the probability is represented by the area under the curve, and we'll need another function. This will be the cumulative distribution function. We will abbreviate that CDF, and it will calculate the area or the probabilities for us. It's also a function, so we'll give it capital F of x. And this is what we'll use to calculate the various probabilities. So let's look at a few different common continuous distributions. So the first is the uniform distribution. The uniform distribution has a shape that is a rectangle. This is uniform. So the curve that defines that is up here, will be this line. This is where the probability distribution function is. It is labeled as the function lowercase f of x, and that is determined by the equation 1 over b minus a, which we'll explain that a little bit later. Then another one that is continuous that we'll learn about is the exponential distribution. It goes like so and decreases and gets closer and closer and closer, but never quite touches the x-axis. This is the exponential. So here is the probability distribution function. This is the curve, the density curve. It is given by a function. Okay, so this is the PDF. It is the lowercase function f of x is equal to, and we'll explain this further later, but it is me to the negative mx. And then we'll be using the normal distribution throughout this course, so just to give a preview of that. Actually, we don't ever usually put the y values there, so let's erase that. We generally just put the x curve, the x line, and it approaches and looks like a bell-shaped curve this direction. So the probability distribution function is this curve. It is the PDF. Okay. And the function f of x that represents that is quite complicated, so we will leave that out for the moment. All right, but remember that this is probability, and we're associating probability with the area under the curve. And the very first criteria that we have is if it's going to be a probability distribution function, the sum of all probabilities must equal 1. So what that will mean for us is that the entire area under this curve and above the x-axis must be equal to 1. So for example, up top here in the uniform, 100% of the area will lie in the rectangle. For the exponential, then 100% will lie here. And it will keep going, getting smaller and smaller and smaller and smaller and smaller and smaller and smaller as it goes out. And in the normal, it will lie underneath this curve, just the same way, and 100% will be in here. Okay, so that's just under because of the criteria that if it's going to be a probability distribution, the sum of all probabilities must be 1, so the area under these curves must also equal 1 or 100% of the data. Okay. So the probabilities of x will be found now in continuous distributions for intervals of x rather than just for a single value of x. So we'll be calculating things like the probability that x is less than some constant, not as we did in the discrete where the probability that x was exactly equal to that constant. Now we can make some distinctions. We can look at the probability in between two values. The probability that x goes in between c and d is the area under the curve, again, above the x-axis. It will be to the right of c and to the left of d. So we can write this in one of two ways. We can say the probability of c less than x less than d, but that will be the same exact probabilities if we include the or equal to's. The probability that c is less than or equal to x, which is less than or equal to d. Okay. So these probabilities, we can come back up here and we have shaded them. So for example, in the first one here, this is the uniform distribution where the probability we're looking that x is going in between 3 and 6. So here's the value of 3, here's the value of 6, and we're looking for the area under the PDF in between 3 and 6. And the same for exponential. Here we're looking for the probability that x goes in between 2 and 4, so it is the area under the PDF in between 2 and 4. And just one more for good measure. In the normal distribution, the area that's shaded here, x is going between 1 and 2. It is the area under the PDF, the probability density function, in between the values 1 and 2. So the thing that is different also about the continuous probability distribution between that and the discrete, remember in the discrete we could say, all right, let's look where the probability of x is exactly equal to c. For the continuous, the probability that x will be equal to some constant has to be 0. So that is going to come down to the fact that there will be no area. So for example, if we're trying to look in between the value of x equals c and x equals c, there is no width. Okay? So area will be determined by length times width, and if there is no width, if there is 0 width, there must be 0 area. So for example, up here in the normal distribution, if we were trying to calculate the area or the probability that x is equal to 0, there is no area to calculate there. And the same would go for all of these. Say, for example, up here in the uniform, the probability that x would be equal to 8 is just this straight line. There is no area for us to shade. And that's also why we will say this, that the probability of c less than x less than d is equal to the probability that c is less than or equal to x and less than or equal to d, because the probability that x is exactly equal to those constants is exactly 0.